In this problem, we're going to get into projectile motion, where to find the initial velocity, the distance to this middle point here, the distance to this final point here, as well as the time to that middle and final point. And those are just two of the same things, essentially, because there's an initial and final time. However, there is a clue about this final velocity that's in the problem statement that's a little bit hidden in a way. And this is the first time, most likely, unless you've already been doing lab before you've watched this, but it's one of the first times that you'll see this kind of indication of the velocity at an apex or the top of a peak. So we'll talk about that in a second, but essentially we're looking for two different values of this projectile motion at two different places in time. We're given the initial time, the initial height, and initial position, because we've defined those all to be 0. The middle height here is 160 feet, and the final height here is 200 feet. And this theta is given. We could have written it over here as a given value in theta, but what theta gives us is the direction of this initial velocity. So I like to write it in terms of that, in terms of the unit vector rather than theta, but you can do whatever you want as long as you understand that the theta is giving you information on the initial velocity, which is one of the things that we're supposed to find here. Okay, anytime you're given three variables, you know that you have to have at least, with three unknowns, you have to have at least three equations. So that is a tip that we'll see immediately. You may have to have more, there may be an intermediate equation, but you know that you have to at least have three. Now you can immediately go and use the equations that you're familiar with in physics, the projectile motion equations, but I'm not going to do that because I want to make sure that you understand where those equations are coming from and how they connect to what we've been doing at the beginning of the semester. So, in order to do that, we start with a free body diagram. And hopefully you're tired of seeing these because you're so good at them and you've practiced them a million times. But the free body diagram that we're doing today is a tiny bit different because there is only one force on it. This is X and this is Y. And that force is the force of gravity acting on that mass. And because there's only one force, it means that the sum of the forces is not equal to 0. So this is the part of the class where we're starting to get into the dynamics. Other than looking at this free body diagram, we're not going to draw like a moment equation. It's a particle. You can't draw a moment equation because r is equal to 0. There's no moment arm to deal with. But we're going to be looking at this right side of the equation and analyzing what's going on with acceleration. So, therefore, there is an acceleration, and we have F equals ma. Classic equation, you know everything comes from that. So, if we were to plug in that one force, we get negative mg, and that is in the j direction, equals ma times the vector of a. If you were to divide out m, then you get negative g in the I direction equals acceleration in the I. And you get 0 in the I direction, sorry. Negative g in the j and 0 in the I. Therefore, your acceleration equation from that free body diagram then becomes 0 and negative g. And for that reason, that is the acceleration that starts off with the problem. So you're not just looking at this and saying, oh, well, it seems like there would be a negative g acceleration here, so we'll put that in there because we know this world acts around gravity and whatnot. Because this could have been a rocket ship, and if it was a rocket, then there would be a force here, force of a rocket, and at that point you would have force of the rocket in the I direction. Then this component would have acceleration show up here. So the acceleration that you find in these equations that we're looking in the dynamics portion, they come from the free body diagrams. They come from this F equals ma. And that's why the free body diagrams are so important in the first part of the class, because they really tie everything together. All right, now let's get up to deriving the projectile motion equations. We're going to start in the x direction. It's easier because it is 0. So ax equals 0. We also know that a equals dvx over dt. If you were to integrate 0 dt equals dv dx. Then you get 0 v f of x minus v naught of x. If you were to solve for that, then you'll find that the final velocity will equal the original velocity. And that equals dx over dt. Now what's interesting here is this is fairly unusual in the real world, because most of the time we have drag or we have friction. It's going to hit the ground and roll at some point. So this is true, but don't think of it as an actual truth. Think of it as a theoretical truth, because you're realistically going to have some kind of F force going on here. But for the sake of this problem, we've assumed that to be 0. Okay, so dx dt. Let's integrate that again. And we're going to integrate this portion of it because we know Vx naught. So Vx naught dt equals dx. And then we get the t showing up here. And we're just going to include t final because we've already defined t naught to be 0. So we don't need to include that. You can if you want to have all the steps, but I just skipped that for now. Simplified down so we can have them nice and on their own. As ax equals 0, v f of x equals v naught of x, and x f of x equals x naught plus v f of x t. And these are the equations that we calculate from acceleration in the x direction. Let's move on to y, and we will look at what we can find from that. From f equals ma, we've defined that ay equals negative g, and it also equals dv dt. If we were to look at just this side and do the integration, we can separate both sides, then integrate that, so we get negative g tf equals vy of f minus vy naught. And we've set, once again, t equal to 0. If we solve for vy of f, then we can get vy of f equals vy naught minus gt of f. And this equation probably looks familiar to you. And vy of f equals dy dt. And we'll integrate this side again. And once we separate it, we'll get vy naught minus gtf equals gtf dt equals the integral of dy. And integrating that, we'll get vy naught t minus 1/2 gtf squared minus y of f, or equals y of f minus y naught. And once again, you may be kind of familiar with this, but you're probably more familiar with the simplified term where y of f is solved for. So that is y of f equals y naught plus vy naught t minus 1/2 gtf squared. So that is probably what you're most familiar with. Now, we'll do the same thing that we did with g, where we pull all of the y equations out. So we'll get a equals negative g vyf equals vy naught minus gtf, and y of f equals y naught plus vy naught t minus 1/2 gt squared. So if we were to also look at the equations again, I'm going to rewrite them down so they're all together, of x, vf of x equals 0, and x of f equals x naught plus v x of f t. So this equation is just a constant. Both of those are constants, even though the constant here is 0. Still, there's not any kind of variable in it. For the velocity equations, for x, it's a constant. It's just a single number. But for the velocity in y, there's a variable t in it. And for that reason, this is v in terms of t. Once we get down to the x position, you get an equation with time in it as well, but there are two equations in y that have the variable t, and only one equation in x that has the variable t. And that's very, very convenient because that ties the two y equations with time. So if you were to solve for time from velocity, then you could plug that in to the y equation and get the value of y from time. You can't do that same kind of substitution in the x because there's only one equation with time. But if you didn't actually feel like solving for the number time in the y equation, you can substitute those equations in and bring this to both of these places. And that is an equation that you'll be familiar with because it's pretty convenient to use. But if you don't want to memorize it or remember it, then you can always solve for time and make your way there. It takes more time, so it's always a good idea to use the shortcuts when you know them. But when you do the substitution for time, you get vy squared equals vy naught squared minus 2g times y of f minus y naught. And now we have a velocity in terms of position in the y. Both of these equations are v equals, but they're very different because there are different components that are inside of them. So we're going to use these equations to solve for what we were given. But before we get into that, I want to talk about how the velocity of y equals 0 at the apex. The apex means the top, and many questions will have a little hint in where the velocity equals 0. If you can't define that the velocity equals 0 at a certain point when the problem is expecting you to, you don't have enough knowns. If we weren't to see that this was equal to 0, we wouldn't be able to solve the problem. So anytime it says apex or top or change in direction, that's an indication that at some point in your conditions, your initial and final conditions, there's going to be a velocity that equals 0. And if we were to graph the problem as a function of y with respect to t instead of y with respect to x, we would find that the parabola would look very similar, which is why they made it a projectile motion rather than something that goes up and down. And at this point, the tangent line is 0. And the tangent line in a y versus t graph is velocity. So at that very, very apex, v of y equals 0. If you were on this side, your v would be positive. If you're on this side, your v would be negative. So at some point you switch from the positive to the negative, and that makes sense. If we were to look at the v of y with respect to t, what that would look like is the point here at the apex is going to be 0. And this side of the graph is positive, so we know it's going to be up here somewhere. This side is negative, so we know it's going to be down here somewhere. But as you get to the top, you'll notice that the slope starts to get smaller and smaller, more flat, more close to 0. And it makes sense that the velocity graph would look something like this. So at the very, very beginning, you have a high y velocity, but it starts to slow down, so it's decreasing even though it's positive. And when we look at the acceleration versus time, at this point, which is negative g, it makes sense because it's constantly a negative acceleration, so your velocity graph is going to be constantly decreasing. And so the position, even though it starts going upward, is going to be constantly slowing down and going back to the negative value. If it had a higher beginning, then it would go taller and come back here, but eventually it would always come back down to the bottom. So notice where the velocity equals 0. That's going to be something you're going to be looking at in a lot of problems. Okay, now that we've gone over that, let's get back to the original problem.